Hello everyone, welcome to my number theory lecture. In this lecture, we continue to study the Euclidean algorithm. It is possible to use the Euclidean algorithm to write the greatest common divisor of a and b in the form ax plus by. Uh, Basically, what it tells us is that we can solve the equation ax plus by equals the greatest common divisor of A and B. This is a particular case of a broader class of equations called the Diophantine equations, particularly in this case linear Diophantine equations. So those equations, the name Diophantine equation is named after the Greek mathematician Diophantus, who extensively studied this type of equations and how to solve them. Right. So in fact, we can find a solution of that this particular type of Diophantine equation, ax plus by equals the GCD of AB, right? By using the division algorithm. More specifically speaking, actually, we first applied the Euclidean algorithm, the division algorithm, and then by working backward, we can actually solve this equation. Right. So to tell you more details, let's get to my notepad. So this is the example we talked about last time. Okay, so I wrote them down, right? So the using the division algorithm, we found the greatest common divisor of 188 and 158, right? Which is 2. Okay, so now this time using this and by working backward, we will find we are going to find you know so here we want to oh so we want to solve the Diophantine equation. 158 times x plus 188 y equals 2. Again, remember, right? 2 equals the greatest common divisor. Okay, the greatest common divisor of 158 and 188. Okay, so this is the example of the Diophantine equation I was talking about, right? Ax, let me use a different, right? So a yeah, I am using a different color. So ax plus by equals uh, the greatest common divisor of A and B. Okay, right. So we start from, so I said we can actually find a solution. By the way, this equation has many, many solutions, okay? But we can find a solution. Uh, and also later on, right now, we are focusing on solving one solution here. But later on, we are going to study, in fact, the finding all solutions. Once we find one solution, then we can find all the rest of the solutions, and we will talk about that later on. Okay, I mean, not in this lecture, but in my later lecture. So stay tuned. Okay, so again, like I said, we can find the a solution of this equation by working backward of this process. Okay, so we will start with the 2. Okay, so 2, I'm going to use a blue color in this case. So start with 2. 2 can be written as, okay, 2 can be written as, here, uh, 2 can be written as 8 minus 6 times 1, right? So 8 minus 6 times 1. Okay, so this equals 8 minus, now we are going backward, right? Again, we are going backward. So this remainder 6, right, can be written as 30 minus 8 times 3. So replace 6 by 30 minus 8 times 3, okay, times 1. I'm not going to write this as like 24, okay? There is a reason why I am keeping a record of each step like this, okay? You're going to see that like, uh, immediately why I'm doing this. Okay, now this can be, this simplifies to, in fact, here I have what? Negative 30, so that's negative 30, okay, and then 8 times negative negative, that becomes positive, right? So, plus, right, we have 8 and 4 times 8, so that's going to be 8 times, I mean, 3 times, right? So 8 plus, 3 times 8, so that's going to be 8 times 4, okay? Right. And again, we're moving backward. So now this remainder 8 can be written as 158 minus 30 times 5, right? So we are going to replace 8 by that. So 158 minus 30 times 5, okay, times 4, okay, times 4. And this simplifies to 158 times 4, right? And I have 20, negative 20 times 30, and I have another negative 30. So that's going to be negative 30 times 21. Now 158, we have 158 times 4, that stays same. And this 30, right? again, we are moving backward. Okay, so here the remainder 30 is 188 minus 158 times 1. So we do the same thing, replace 30 by that, right? So negative, instead of 30, I have 188 minus 158 times 1, okay, times 21. So this simplifies to 158 times 4. Oh, no, it's not, right? That's not it. I have more, right? So I have negative, positive, right? 158 times 21, and I have 158 times 4. So together, that becomes 158 times 25, right? Plus 188 times negative 21. Okay, so now you see that we actually solved this equation. Okay, we find a solution. So as you see, x equals 25 and y equals negative 21. Okay, is a solution of this equation, right? 158 x plus 188 y equals 2. It's pretty neat, right? Okay, so that's basically what I just did, right? So the this example here in my slide. All right, so let's move on. So here comes something called Bézout's lemma. This is named after a French mathematician, Bézout. So here's the theorem, okay? Where I called it theorem, but it is called Bézout's lemma. So maybe I should have said it like a lemma, but anyway, theorem, fine. But it is called the Bézout's lemma. If A and B are integers such that the greatest common divisor of A and B is defined, then there exist two integers x, y, such that, the greatest common divisor of AB equals AX plus BY, right? We just demonstrated that how we can find a solution. Okay. Now in this equation is called Bézout's identity. Bézout's identity. This particular solution. But like I said, we are going to study more about linear Diophantine equations. I mentioned the linear because these are not only kind of like Diophantine equation. There are like more different types of Diophantine equations. For instance, like quadratic Diophantine equations also. Okay, so but this is actually a special case of more broader class of equations called linear Diophantine equations. Okay, and corollary, if D is any common divisor of A and B, not both of which are 0, then D divides the greatest common divisor of A and B. This must look, this statement, this corollary must look familiar to you. In fact, we talked about it in my earlier lecture, okay, one of the earlier lectures. Uh, in fact, in my first lecture, I think, right? So we talked about this, and then you know, I also proved this corollary, assuming that this the Bezo's lemma, right? I, yeah, I proved this. So in case you don't remember, right? I want you to go back to my first lecture. Okay, and here's a definition. We say K is a linear combination of A and B if there exist two integers xy such that K equals AX plus BY. We already know this, right? I have been using actually the term linear combination over and over again by now. So, but I just formally introduced as definition here. Okay, so here's another theorem. Given integers a and b, non-zero integers, and m, if a divides m and also b divides m, then the least common multiple divides m also. You may somehow see some connection, a relationship between this and previous corollary. Okay? In fact, if you thought so, you are right. So what's the relationship? What's the connection? In fact, this corollary and this theorem are dual to each other. What do I mean by that? I mean they are dual to each other by, uh, you know, if you, I went too far. Oh. If you replace it, the inequality, okay, if you replace inequality and there's corollary, you get this theorem, and vice versa. In this theorem, you reverse it, you replace it, you reverse inequality, then you get corollary. So that's what I meant by, the corollary. The preceding corollary and this theorem are dual to each other. So basically, by proving one, you prove this, okay? And all you have to do is just you reverse the inequality. So this is also an important theorem to know. Okay, so moving on. Right, so a little more about the linear Diophantine equations. Okay, a linear Diophantine equation, ax plus by equals c, is solvable if and only if the greatest common divisor of a and b divides c. Now, this statement is not difficult to prove. Okay, in fact, this will be introduced as a theorem later on, right, in my next lecture. In one of my following lectures, right? And the proof will be left as an exercise, okay? In you know in one of the problem sets, upcoming uh, in one of the upcoming problem sets, right? But the proof is not easy. If I give you a hint, okay, so only if part is straightforward, you know, so the Oh, actually, the what is that? Oh, if part is straightforward. So if part means that if the greatest common divisor of A and B divides C, okay, divides C, then since the greatest common divisor of A and B divides A and divides B, so it's gotta divide the C. So that's easy, right? Only if part. So this direction, right? Only if part. Right. So assuming that this is solvable, yeah, you gotta. Oh, I'm sorry. I'm sorry. I got it backward, right? I got it backward. Only if part is straightforward. Sorry about that. Okay, so let me repeat that. So this only if part, right? That's straightforward. Let's assume that ax plus by equals c. Ax plus by equals c uh, uh, is solvable, means that there is a solution. So this equation itself, that makes sense, right? Okay, so well, in that case, the greatest common divisor. The explanation is same, but the direction of a proof statement it was wrong. That's not the if part, only if part. So this direction, okay. So assuming this ax plus by equals c is solvable, right? So we claim that the you know the greatest common divisor of A and B divides C, right? So that's only if part, right? So again, like I said, if this is solvable, a solution exists. So this whole thing makes sense, right? So in that case, the greatest common divisor of A and B divides A and divides B. So it's gotta divide C. So that's straightforward. The other way around, the if part, okay, the other way around, that's if part, assuming this. So, the greatest common divisor of A and B divides C. With that assumption, we have to show that this Diophantine, linear Diophantine equation is solvable, right? That's not difficult to show. I'm gonna, here, I'm gonna give you a hint. A hint is use the Bezo's lemma, okay? Use the Bezo's lemma we just talked about, okay? That's the hint. All right, so this statement is true, right? So what I'm actually going to talk about next is what will provide an algorithm to solve this Diophantine equation using this statement. Okay, using this statement. So I mentioned an algorithm, right? In fact, you can implement that algorithm, say, as a computer program, like for instance, a Python program. Okay, so we are gonna talk about that, the computing aspect of what we discussed, in my preceding lecture and this lecture. Okay, so using two uh, software packages like one Maxima, that's the a computer algebra system, and the other one is in fact a computer programming language called Python. Okay, so we are going to talk about that in my following next lecture. And this process actually provides the an algorithm to solve this linear Diophantine equation using this statement. Okay, so to talk about it, let me get back to my notepad. Okay, I'm gonna repeat writing uh, the statement. Yeah? So ax plus by equals c is solvable if and only if the greatest common divisor of a and b divides c. Okay, so for now we are just assuming that this is true. It is true. Okay, right, and you can easily prove it. I gave you a hint also, right? Okay. All right. So we are going to talk about that algorithm. Okay. Right. So here's the first case. So if right, if B divides A, okay, if B divides A, then of course the greatest common divisor of A and B is going to be just B. So in this case, you know, uh, and in this case, x equals 0 and y equals c over b. C over b in this case, although I'm using division notation, okay, this is an integer because the greatest common divisor of a and b equals b, so b divides c, right? B divides c, so this is an integer, right? We deal with only integers in number theory, okay, right? So, you know, this is an integer. It's a solution, okay? It's a solution. Okay, well, I just actually mentioned something like, actually incorrect. I said something like what, we deal with only integers in number theory. Okay, that's it. Only partly true, right? For now, we are only dealing with the integers, but we also deal with the rational numbers as well. Okay, we also deal with the rational numbers as well, but not now. Okay, perhaps later. But for now, we are just dealing with only integers. Okay, right? So yeah, I just wanted to correct that. Okay, so this case is done. What if it doesn't divide? If B does not divide A, then here, we are assuming that B is greater than, okay? So, here we are assuming that B is greater than A. If not, doesn't matter. Then, you know, uh, where I'll explain why it doesn't matter, right? So anyway, so assuming that B is greater, no, I'm sorry. Here, A is greater than. By assuming that A is greater than B, you can divide the A by B. So A equals BQ plus R. BQ plus R. So here, assumption here is that A is greater than B. What if the other way around, like B is greater than A, no big deal, then just changing A and B, and the rest of the argument is same. Okay, not a problem, right? But here also, actually in this case, where maybe I should start with, yeah, I already used this assumption, right? I already used this assumption. So in the first case also, I consider the case what B divides A, right? So I already used the assumption that uh, A is greater than B. So implicitly, right? Implicitly, I use the assumption. So here the assumption is assume that A is greater than B. If not, if the other way around, if B is greater than A, it doesn't matter. All you have to do is just swap A and B, right, for the rest of the argument. Okay, so not a big deal at all. Okay, so moving on, right? So A equals BQ plus R, right? So in this equation, AX plus BY equals C, replace A by BQ plus R. So we have BQ plus R times X plus BY equals C. Now this equation can be rearranged to the following equation. Okay, so B times Q X plus Y plus R times X equals C, right? Okay, that's it, simple algebra. And by setting I'm going to introduce new variables. So U equals Q X plus Y and V equals X. Okay, this equation can be written as uh, what is that? BU BU plus RV equals C. So we actually, end up getting what? Another the linear Diophantine equation with these new variables, right? U and V and the coefficients B and R. Okay. In fact, we can repeat the process. We can repeat this process. So let's do that. Okay. Right, to have like a better picture of the how this works. So I'm out of space, so I'm moving to next page. Right. So here, let me go back uh, because I gotta mention something. So our new Diophantine equation has what coefficients B and R, right? B and R. Since the greatest common divisor of B and R is same as the greatest common divisor of A and B. We know that, right? And we already know the greatest common divisor of A and B divides C. So the greatest common divisor of B and R, of course, divides C, right? So, the equation uh, BU plus RV equals C is solvable. Okay, is solvable. In other words, there is a solution. Okay, and if we can solve it, if we can solve this equation, we can uh, we recover a solution of the original equation as, of course, original equation means ax plus by equals c, right? So we can recover a solution xy of the original equation as x equals v and y equals u minus qv. Okay, right. Okay, so now for this equation here, so bu plus rv equals c. Again, we can consider two different cases. If R divides, okay, if R divides B, then the greatest common divisor of B and R is R, right? Is R. Okay, and right. So, and in this case, we have what is that? The u equals 0, u equals 0, and v equals c over r, c over r, okay? Because, we already know the greatest common divisor of b and r divides c. And in this particular case, the greatest common divisor of b and r equals r, so r must divide c. So c over r is an integer, okay? We want integer solutions of these, right? Okay, good. So we got this one, right? So we can find the solution. And in this case, the what is that? uh, we can recover, the solution of the original equation, right? We recover a solution of the original equation as x equals c over r, c over r, and y equals negative q, okay, negative q times c over r, okay? Both x and y are, of course, integers, okay? So here, that's times. Okay, good. What if r does not divide r does not divide b, right? R does not divide b. Then in this case we know that b is greater than r, right? B is greater than r. So the b, we can divide b by r. So we have b can be written as r times q1 plus r1. Okay, and by replacing, here's the equation, right? So bu plus rv equals c. Okay, so by replacing b by this guy here, okay, or substitute this into this equation, right? Bu plus rv equals c. We obtain b times what is that? R q1 plus r1 plus rv equals c. Okay, right. And this equation also, is rearranged to uh, b times, oh, no, that's not what I want. That's not what I want. So this equation can be rearranged to r times bq1 plus v. I did something weird. No, I substitute this into b, right? Substitute this into b, and so how the heck I still have b, right? No, this is incorrect. Sorry about that. So b shouldn't be there. Instead, what did I miss? I missed u, right? So I missed. Yeah, that sounds funny. I missed u. Okay, so I missed the variable u, right? Okay, so this can be rearranged to rq1. So this has to be fixed also. Q1 times U plus V, right? And plus R1 U equals C. Okay, so here we set, by introducing new variables S and T. So here S equals, set S equal to Q1 U plus V, T equal to, set T equal to U. Okay, then we get a new equation in terms of the new variables S and T. So R S plus R1 T equals C. So we get this linear Diophantine equation. Since the greatest common divisor of R and R1 equals the greatest common divisor of B and R, and which equals the greatest common divisor of A and B. So this guy divides C. So this equation, right, here, RS plus R1T equals C is solvable. Okay, that's solvable. Maybe I should have used some equation numbers, but that's okay. Right. If we can solve it, all right, so if we can solve this equation, okay, if we can solve this equation, we recover a solution of the preceding step. Okay, what I mean by that, this equation here, BU plus RV equals C, right? So let me write that down. Solution of BU plus RV equals C as same process, right? So U equals T and V equals S minus Q1 times U. Okay? So as you can see, this process can continue. Okay, this process can continue, but not indefinitely, right? According to Euclidean algorithm, right, or division algorithm, that the process must terminate, right? Okay, so this process terminates according to the Euclidean algorithm with an equation where the second coefficient divides the first, right? So the first case. So eventually, we are gonna get there. So that's when the program stops and we find the solution. Okay, using this algorithm we find the solution of this original linear Diophantine equation. Okay, folks, so this is it. And more details of my discussion in this lecture can be found in my lecture note at the following address, which is pretty long, but it's hyperlinked. So all you have to do is just click on this, the URL, right? It'll take you there. And also, if you want to visit my just main blogger site where you can also find like lots of my lecture notes in many different, other subjects. So just click on this word blogger, which is hyperlinked. So it'll take you there. And also there is a problem set for the discussion we had, right, in my preceding lecture and this lecture, right, about the division algorithm. So number 30 problem set 1 about the division algorithm is available at the following address. Pretty complicated URL, but that's okay. This is also hyperlinked, so all you have to do is just click on it and it'll take you there. Thank you very much for listening and watching always. Okay, thank you. Bye-bye.